Organic synthesis is a very large part of chemistry. If you move on and look at the branches of chemistry, there is an area of organic synthesis, making drugs, making synthetic materials. There's tons and tons of money poured into this area of chemistry. We're going to look at 5 basic organic reactions that can be used to synthesize simple organic molecules. So it's very much an introduction into organic reactions. At this stage in your chemistry career, you're probably going to feel a little bit like there's a lot of memorizing to be done when it comes to organic reactions. You need to recognize what the substances are that you're combining. You need to recognize which type of reaction is going to occur, and you need to apply the rules. What I will do in my discussion of organic reactions is my best to help you to visualize and see so that you can predict using a little bit of logic rather than pure memorization in order to know your organic reactions. But when it comes down to it, unfortunately, there is a bit of memorizing to do. The first main type of reaction that you'll encounter is what's called an addition reaction. This involves some kind of multiple bonds, whether a double bond or a triple bond, and that bond is going to be broken and other substituents are going to be added. The kinds of things that we can add across the double bond, we say, are hydrogen halogens, which we simply refer to as X2, water, or hydrogen halides, or HX. We're going to start with 2 reactants, and we're always going to end up with 1 product in these addition reactions. And you're going to see that we're going to apply an important rule called Markovnikov's rule, and we'll discuss that through some examples. So here are several examples of addition reactions. We've got our double bond and the substance that we're adding. And what happens is, in this case, the bromine is going to be added across the double bond. So the way that I imagine this is I think of the bromine as going over top of the double bond. Any chemical reaction involves bond breaking and bond forming. So in this case, what's happening is this double bond is being broken, and this single bond holding the bromines together is being broken. And those electrons are essentially being used to form the bond between the bromine and the carbon. So as you can see, what we're left with is 1,2-dibromobutane. In this case, we're adding HBr across the double bond. So we've got our hydrogen and our bromine, and it's being added across the double bond. Now in this case, you have a choice. I could write the HBr in this way, or I could have written the HBr the other way around, so the bromine here and the hydrogen here. In actual fact, if this reaction were to occur, there would be a mixture of the products. One of the products, though, is referred to as the major product. And this is the product that we're going to show, is the major product. And what we're going to do to decide what the major product is to apply Markovnikov's rule. Markovnikov's rule states that when you have an addition reaction, the substance other than hydrogen, so the bromine, okay, in this case, or you'll see when we add water, the hydroxide, it's going to add to the most substituted carbon. So we have to talk about what that means. We've got 2 carbons here, this one and this one. And the hydrogen is going to end up adding to the least substituted carbon. So this one here, when we talk about the substitution of the carbon, we're talking about how many other carbon atoms, or basically atoms other than hydrogen, are attached to that carbon atom. So in this case, this one is mono-substituted. There's one other carbon attached to it. while this carbon here, the second carbon, is di-substituted. It's got two carbons attached to it. So the second one, being the more substituted one, is going to hold the bromine atom. The reason for this is that in the mechanism of the reaction or the process of the reaction, the hydrogen is actually going to attach first, and it's going to use the electrons from the double bond in order to form the bond. And what we're left with as an intermediate of this reaction is what we call a carbocation, a positively charged carbon, which is really unfavorable and unstable. And because it's so unstable, it would rather be in a spot that's more substituted or surrounded by electrons, okay, from other carbons. So this is a more stable carbocation. Okay, so this is the bromine that attaches there. Now, that little discussion about the carbocation and the mechanism and stuff like that, that's what I'm talking about when I say we're going to use a little bit of logic, but the reality is you just need to memorize Markovnikov's rule. Okay? You're not going to be asked any questions about the mechanism. Okay? It takes a year of organic chemistry to learn all the detailed mechanisms of organic chemistry, and that's not the focus of this course. In this example here, when we add water, this computer program writes it as OH2, but this is really just H2O. What we're adding across the double or triple bond is hydrogen and OH. In an organic molecule, it's not hydroxide that we're adding, it's the hydroxyl group. So we're essentially making an alcohol. This is another type of addition reaction that requires us to apply Markovnikov's rule. The two substances we're adding are the hydrogen and the hydroxyl. The hydrogen goes on the least substituted carbon, and the hydroxyl goes on the most substituted. Okay, so that is why the OH is on the second carbon here. In this third example, we're adding iodine to an alkyne, which has a triple bond. And you'll notice I'm adding only 1 mole of the iodine. So when I add across this triple bond, I'm left with a double bond. If I were to add 2 moles of I2, I would be left with a tetraiodo compound with the 4 iodines. The first mole would be added across, breaking the double bond, and then the second mole would be added, breaking that other bond. So these are the basics of addition reactions. Substitution reactions are partnering reactions to the addition reactions. They're not the opposite, but they apply to different compounds. So addition reactions applied to alkenes and alkynes, which were both hydrocarbons or had the multiple bonds. A substitution reaction is going to occur with our other hydrocarbons, which are the alkanes and benzene. Alkanes are pretty unreactive, and that's why they'll undergo a substitution reaction. Okay, it's the multiple bond in the alkenes and alkynes that really make them reactive. It's this pair of electrons that is just looking to react with something or share with another atom that's coming by. With an alkane, it's nonpolar. There's really no need for it to react. So we're going to need some UV light for these substitution reactions with alkenes. Benzene, okay, let's just discuss why benzene will not undergo an addition reaction. If benzene were to undergo an addition reaction, so if I tried to add Br2 to it and it underwent an addition reaction, okay, what we're doing is we're losing the aromaticity of the benzene. And the aromaticity, or this alternating double single bond, is what makes benzene so stable. Okay, so this reaction will not actually occur. When benzene reacts, it wants to maintain its aromaticity, okay, or this alternating double single bond. So if you've got an alkane and you're going to have a substitution reaction, essentially what a substitution reaction is instead of something being added, something's being substituted. So we're going to add halogens, and what's going to happen is we're going to substitute one of the hydrogens in the alkane for a bromine in Br2. And what the UV light does is it actually helps to cleave or to break this bond. Okay, it breaks it, so it makes a very reactive bromine. And so then what happens is the bromine is able to bond with the hydrogen, okay, to make HBr. One of the bromine atoms will do that. The other bromine atom will attach onto the alkane. Now, this is another reaction where you're not going to get a pure product because this substitution could really occur anywhere in the molecule. So it's not an ideal reaction for synthesis, but it's important for learning reactions in early stages. As I talked about with benzene, okay, it doesn't want to lose its aromaticity. So if you react it with bromine, rather than having an addition reaction, what's going to happen is we're going to have a substitution reaction. Okay, so one of the H's on the bromine will go off and form HBr, and the other bromine will attach to the molecule. In this case, no matter where the substitution occurs, the molecule is going to be the same. It's going to be 1-bromobenzene. Okay, so this is a pure product. The catalyst that's needed for this one is FeBr3. Okay, it helps to promote this breaking and forming of the new bonds. Okay, we're not going to discuss this reaction. The last reaction that we'll discuss in this first part is elimination reactions. Elimination reactions are the opposite of addition reactions. So rather than adding something across the double bond, we're going to remove substituents and form a double bond. So we're going to start with one reactant and we're going to break it up and produce two products. We're going to look at one particular type of elimination reaction. There are many, and that's the dehydration of an alcohol, okay, which is the removal of water, and we need sulfuric acid as a catalyst to do this. Okay, so if we've got an alcohol and we add sulfuric acid and heat, we're going to be able to dehydrate this alcohol or remove water from it. So what we're doing is we're removing the hydroxyl and the hydrogen from a neighboring carbon. These will leave to produce water. And because we're losing this bond and this bond, okay, we're left with a double bond in the molecule. Okay. When you study organic chemistry in university, what you do is you study the mechanisms of these reactions. You follow the electrons through the reaction from beginning to end. In some ways, it makes it much easier to understand the reactions, okay, but it is a lot of information and there's a lot of things that we need to do to get to that point. Okay, so that's going to conclude the first part of the reactions lesson. Okay, we discussed addition, substitution, and elimination reactions. Okay, in the next lesson, we'll talk about oxidation and reduction reactions, which are opposites of one another, and condensation and hydrolysis reactions, which are opposites of one another.